In this module, we are going to derive formulas for entropy change in certain thermodynamic processes. In order to calculate the entropy change between two states labeled as state 1 and state 2, we must integrate this ratio along a reversible path. Entropy is a state function, which means the entropy change we determine for a reversible path is the same for an irreversible process. For a start, we consider a reversible adiabatic process. During any reversible adiabatic process, there is no heat transfer between the system and its surroundings. This results in a zero entropy change for that process. Now let's look at another typical state change, an isothermal expansion or compression of an ideal gas. As a system, we consider n moles of ideal gas. Its state 1 is characterized by pressure P1, volume V1, and temperature T1. State 2 is defined by P2, V2, T2. The state change is isothermal, meaning that T1 is equal to T2. We denote both temperatures as T. To calculate the entropy difference between these two states, we must consider any reversible path from the initial to the final state. Importantly, the entropy difference will be the same no matter how the state change was actually carried out. It could be a reversible volume change in a single process. It could be an irreversible volume change or any sequence of processes. The entropy difference depends only on the initial and the final state. A simple reversible path leading from 1 to 2 is a reversible isothermal volume change in a single process from V1 to V2. According to the first law of thermodynamics, du is equal to delta Q plus delta W. The internal energy of ideal gas depends solely on the temperature. Therefore, it does not change in an isothermal process. Thus, along this path, the heat exchanged between the system and the surroundings is always equal to the negative of the work done. Considering that ideal gas does only volume work and the external pressure must be equal to the internal pressure in order to satisfy the condition of reversibility, delta Q is equal to P times dV. Here, the volume of the gas is the variable that describes the progress from the state 1 to the state 2. Using the ideal gas law to express pressure, we obtain the following expression for delta Q, nRT over V times dV. The total differential of entropy is delta Q over T, or 1 over T times nRT over V times dV. This can be simplified to nR over V times dV. The entropy difference between states 2 and 1 is the integral of ds over the reversible path expressed as the change of volume from V1 to V2. Using the previously obtained expression, we can express ds as a function of volume V. Since nR does not change along the path, we can factor it out of the integral. After the integration, we obtain the following expression: nR times the logarithm of V2 over V1, or nR times the logarithm of P1 over P2. Note that the entropy change is positive for an expansion and negative for a compression. How does entropy change if we change the temperature? Let us first look at an isobaric temperature change. Imagine a system transitioning from one state, which we will refer to as state 1, with a pressure P1 and temperature T1 to another state, state 2, defined by pressure P2 and temperature T2. Given our isobaric conditions, the pressure P2 remains equal to P1, and we can refer to both pressures as P. A reversible process that takes us from state 1 to state 2 is a reversible temperature change at constant pressure. We consider the system to be characterized by its heat capacity at constant pressure, Cp. The heat exchanged during this reversible process, delta Q ref, is given by Cp times dT, where dT represents a small change in temperature. We can calculate the differential of entropy ds as the heat exchanged in this reversible process divided by the current temperature T. This can be expressed as ds equals Cp over T times dt. To obtain the total entropy change, delta S, between our two states, we integrate ds with respect to temperature from T1 to T2. That means integrate Cp over T times dt from T1 to T2. This integral can be evaluated analytically if Cp is a known function of temperature. If the heat capacity Cp is constant over the temperature range, the equation simplifies. The entropy change, delta S, can be expressed as Cp times the natural logarithm of T2 over T1. Now let's consider how entropy changes when there is a temperature change at constant volume. This process is analogous to the isobaric temperature change we discussed in the previous slide. Picture a system transitioning from one state, state 1, with volume V1 and temperature T1, to another state, state 2, defined by volume V2 and temperature T2. Given isochoric conditions, the volume remains unchanged. The path we are considering is a reversible isochoric temperature change. Just as before, we described the system in terms of its heat capacity. This time we consider the heat capacity at constant volume, denoted as Cv. The entropy change between the initial and final states can be calculated by integrating Cv over T with respect to temperature T, from T1 to T2. If Cv is constant over the temperature range, the entropy change is given by Cv multiplied by the natural logarithm of T2 divided by T1. In many real-world situations, processes don't change just one parameter at a time. Instead, multiple parameters may change simultaneously. How do we handle such cases? Recall from our previous discussions that entropy is a state function. This means its change depends only on the initial and final states, irrespective of the path taken to get from one state to the other. Given this property, we can strategically choose paths that simplify our calculations. For example, any simultaneous change in temperature and pressure can be decomposed into two segments: an isobaric temperature change and an isothermal change of pressure. The strength of this approach is its straightforwardness. After breaking down the total process into these two segments, we can calculate the entropy change for each one independently, just as we discussed in the previous slides. To find the overall entropy change for the combined process, we then simply sum up the two separate entropy changes.